and human-centered computing. She spent a decade at the National Center for Supercomputing Applications, where she was the director of the Advanced Visualization Lab and director of the Visualization Program Office. You may have seen her work in IMAX films, planetarium domes, New York Times articles, and viral social media. She's also a long-term volunteer with the ACM SIGGRAPH community and currently serves on the executive committee. And recently she returned to work on a PhD at the University of Utah, and I had the great privilege of working with Kalina this past summer for a research internship with our HAI and visualization team. Kalina impressed me in many ways during her internship with us, but one aspect that especially stood out to me were her great research communication skills, in particular with the research video that she made for our paper submission. So I'm also super confident that this will be a fantastic talk. So with that, I'll hand it over to Kalina. So please take it away.
Thanks so much, Yo. So with this talk, I'll primarily be focusing on the work that I did going back to school. So I work with the Advanced Visualization Lab at the National Center for Supercomputing Applications. So I'll be talking to you about cinematic scientific visualization. And kind of to kick things off, I want to start by maybe introducing you to a couple related but distinct terms. Within the world of scientific imagery, there are a few different ways that a scientific concept could be communicated. Very commonly, you'll see scientific illustrations that are created by artists, like this planetary collision that we're looking at right now, created by artists at NASA. On the other end of the spectrum is data visualization, which is often created by scientists for purposes of analyzing data, understanding simulations that they might be running, or data collected from the real world or the universe. So again, here is a planetary collision. In that format, these look very different from each other, and they serve very different purposes. Traditionally, visualization tends to be more for analysis, and illustration tends to be more for communication. But the sweet spot in which a lot of my work lives is in the middle, what I call cinematic scientific visualization, which does visualize scientific data sets, but uses filmmaking tools like Maya, Houdini, things that are more often seen in the film industry, and applies those techniques and tools to the scientific data. So this visualization that you're seeing in the middle of the planetary collision is exactly the same data as the one on the right, but it is much more cinematic and is intended to be used for public communication of this data. So creating these types of visuals requires combining in basically equal parts science and art and technology. And the Advanced Visualization Lab that I used to lead had a combination of people across these areas. We were about 50% artists, 50% programmers, and we brought in scientists depending on the projects that we were working on that were experts in that specific area. So here are a number of films that I've contributed to in my time with the AVL. A lot of these are things you might see on Amazon Prime or streaming services. There's some IMAX films and some immersive planetarium dome shows as well. So I'll start by playing a brief demo reel that showcases some of this work, and I hope this has sound. Let me know if it's not coming through. So everything in this video was a data visualization based on real accurate science, worked on in collaboration with scientists and validated by them. Creating these types of visuals requires a bit of a complex pipeline, and for kind of more technical talks, I often dive into, all of these steps of this pipeline, but this is not a technical talk today, so I'm going to simplify what all of this entails into saying that it involves solving three different types of overlapping challenges. And I'll cover these one by one with some examples, starting with communication challenges. The target audiences that we're trying to reach are incredibly varied, ages 8 to 80, of all backgrounds, all over the world. These documentaries often get translated and shared worldwide. So you might imagine that communicating a piece of information to such a wide range of individuals comes with some challenges. So I often like to show this comic showing there's a professor at a podium saying there is an eye at the center of a hurricane. And there are three very different interpretations of what that means. And this, I like showing this because I think it's a really great illustration of the fact that even when you think that you're being very clear in how you're communicating something, people will often interpret that in very different ways. And sometimes they can be difficult to guess what those ways might be. So things like this require, testing and talking to your audiences and understanding them and making sure that you're actually conveying the message that you think you're conveying. As an example of this, I want to walk you all through a thought exercise of a visualization that we did once to visualize the process of photosynthesis. So if we start by just thinking, okay, well, what are the steps that a plant goes through or whatever organism goes through to do photosynthesis? Now, it starts with a photon hitting a chlorophyll. The chlorophyll gets excited, the electrons are activated, water splits, and many, many things happen. But let's just focus on this very first step. So in order to tell the story of photosynthesis, we have to start with a photon hitting a chlorophyll. Now, how do we actually show that? Breaking it down even further, we have to start by showing a photon. And if you've ever taken a quantum physics course, you might be familiar with the fact that photons exhibit wave-particle duality. They are a quantum phenomenon. This is not necessarily something that could easily be explained to an 8-year-old in our audience, or even an 80-year-old. This is kind of a pretty advanced topic, but it is the most basic thing that we need to start with in order to tell the story of photosynthesis. So how do we do this? We really can't spend, an hour giving a lecture on quantum theory just so that we can explain photosynthesis. That's not really the goal of the story. Even though this is an important part of the story, we have to think about this a bit differently. We started by doing a bunch of different tests of, how can we simplify what a photon might look like? Some of these exhibit wave-particle duality, or we're trying to kind of make them a little bit wavy. Some of them are more abstract. There's one that, is just light rays where we don't really try to touch on that at all. With visualizations like these, you need to recognize that sometimes accuracy is impossible and maybe not really the goal. Explaining photons to an 8-year-old is just not ever going to be worthwhile. So it's not something that we try to do. So it takes a lot of iteration to figure out, how to best communicate this while being as accurate as possible and recognizing that some things need to be simplified to an extent that isn't necessarily going to make it accurate. So I've come up with this hierarchy of needs for these types of visualizations. Above all else, including above accuracy, the visualization needs to be understandable. That is the most important thing of all. Once it's understandable, then you can focus on accuracy, and both of those needs must be met before you can focus on it being appealing and beautiful. Even though that's kind of the signature look of these visualizations, is their visual appeal, that really is kind of just the last part of the process. It being understandable and accurate are much more important than the way that it looks. In terms of the way that it looks, any data set can be represented in a different number of ways that makes it look completely different. So here we're looking at two visualizations of a tornado, one which is more abstract on the left and one that is more photorealistic on the right. And these are both very similar data sets, but depending on what the goal of the video is, how it's going to be presented, to whom, what types of feelings we're trying to evoke, we might make very different design decisions to make these look so different. The one on the left is perhaps a bit more, technical, and it's going into the story of how a tornado forms so that we can understand the processes inside it. Whereas the one on the right focuses more on the emotional aspect of it, that tornadoes are big and frightening, and this tells a very different story depending on the design choices made. In order to make sure that the visualizations are as accurate as possible, because as I mentioned, they can't necessarily be fully accurate, we don't want to be the ones making those decisions of where it's okay to, fudge some certain things, where it's incredibly important to stay true to the data. We work very, very closely with scientists who are experts in these fields. They help us come up with the overall story and script that is told, and they validate the visualization and the design decisions that we make along the way, just to make sure that everything that we're communicating and doing is representative of their work. In addition to talking to scientists, we also talk to our audiences, as I alluded to earlier. Sometimes our audiences get confused about where the imagery is coming from. This is something that we learned from doing some earlier tests. We found that sometimes people had a hard time telling apart whether the video they were looking at was real video captured through something like a telescope, or a visualization, or an artistic drawing. So once we learned that this is something audiences struggle with, we started to come up with ways of better conveying that this is a data visualization, both in terms of what we tell them and how we actually visualize the data as well. So we've done audience tests through surveys where we show kind of different versions and ask people what they thought of it. We've done focus groups with people where we have here, we're showing kind of an early color test where, one image is just slightly more saturated than the other. We also do a lot of, informal presentations and talks to our audiences. We've done LLM-based analysis of reviews that people have left on our YouTube and Amazon Prime videos to kind of get a sense for the sentiment analysis that people have for the finished products. And we use all of this to make our visualizations more accurate and better and more understandable. So with that, let's move on to technical challenges. A problem that I think all computer adjacent people are familiar with is that big data keeps getting bigger. And this is true for the data sets that we visualize as well. Here I'm showing the, I just blinked on what this telescope is called. Oh, the Vera C. Rubin Observatory. And this is expected to produce 20 terabytes of data every single night. So, these are just such vast numbers. Processing this data is challenging. Visualizing this data is also challenging. Here's a specific example of a data set that we visualized that was 200 terabytes and took the scientist 1.5 billion hours on the Blue Waters supercomputer to process and assemble. This is a data set that's an Arctic digital elevation model. So a representation of height of every piece of land in the Arctic at a resolution of 2 meters. And we did work with a subset of the data, only 45 terabytes for the final documentary. But still, this also took rendering on a supercomputer, 110,000 hours just to render the final visualization that we created. Another problem is that data is not only big, but data is messy. This is a zoom in to the Arctic data set that I just showed, where there's one region where there's a melting ice cap. The videos along the top are the original data, and then along the bottom are cleaned up data. And in the originals, you can see these kind of messy patches popping on and off. And this is where clouds have gotten in the way between the satellite that's collecting the data and the ground where we're trying to collect the data. So this results in errors where we're incorrectly representing the height of the land as the height of the clouds. So when we started working with this data and wanted to visualize this in 3D, we would get these terrible, massive, ugly spikes where, again, those were clouds that high, but in the data set, they were represented as land. And obviously, this is completely unacceptable for putting into a documentary or in front of the general public. The spikes, as well as other issues with the data, required a lot of cleaning. And we developed a machine learning model to help us with this data cleaning. And in the end, after lots of manual cleaning and labeling, and then a little bit of ML help, here is the final kind of cleaned version of this, where everything looks smooth and beautiful, and you would never know how much work went into just getting it to look this way. Oh, and I'm going to play a little behind the scenes making of video to show you more about what it took to create this.
Here's what went into making a piece of Atlas of a Changing Earth. We built on the results of the Arctic DEM survey project. That survey used high-resolution satellite imagery, hundreds of thousands of observations spanning several years, and measured the Earth's shape in fine detail, covering all the land north of 60 degrees latitude. Transforming that imagery into this mapped dataset of Earth's topography required millions of hours of Blue Water's supercomputer processing. Satellite observations were in strips, a few kilometers long. Throughout the survey, many areas were observed on dozens of occasions, revealing how Earth's topography changes with time. This shot from Atlas of a Changing Earth animates the multi-year Arctic DEM survey in the context of a realistic-looking Earth. The visualization incorporates seasonal changes in Earth's appearance. We created it in layers. On the ocean is a climate model simulation of sea ice coverage. To design the unbroken animation path around the world and into Vavilov, we used AVL's interactive Virtual Director software. Virtual Director shows a simplified preview of the scene in the correct 3D location. Final rendered elements fit right in. Datasets, camera paths, and so on are brought into the commercial software tool Houdini from Side Effects. Its node-based architecture supports a mix of programmable and interactive design. The DEM survey data shows exquisite detail, but contains many artifacts, thanks especially to clouds. Seen in a 3D landscape, every defect becomes even more prominent. Lots of manual work went into cleaning the raw survey data, masking out clouds and aligning strips with each other. The DEM data was observed at discrete times at irregular intervals, days or months apart. To give the sense of continuous motion, we used morphing interpolation in Nuke on the high spatial frequency ripples in the collapsing Vavilov ice to create three-dimensional evolving topography. Here's what went into that. Starting from a flat version of the landscape, we add the time-interpolated topographic relief and use Landsat optical imagery to provide color. It too is interpolated over time. Over wintertime darkness, we again alter the landscape color and lighting, and the sky, to suggest dim twilight. As springtime returns, so does Landsat imagery. The sun's very low as spring begins, so the early Landsat images are tinged pink with sunrise.
Sorry to cut that a little short, but just credits at the end. So another challenge that we often deal with is large changes in scale. In the previous video that I showed, the visualization starts out looking at the whole Earth and then zooms in seamlessly to look at this one small ice cap. And this is something that we do a lot. There was once a visualization that we made where we started at the Earth, zoomed out to look at the solar system, then to the Milky Way, then the entire observable universe, all in one seamless camera move. Going across all of these different scales. Of course, there isn't a single data set that allows you to do that kind of zooming, but we very often combine multiple data sets at different scales that are embedded within each other so that we can create these exciting, beautiful journeys But going through, numbers this large, you often get floating point errors or just kind of other technical challenges regarding scale that creative solutions also need to be found. Another challenge is that, especially when working with real data or data that's been simulated on a supercomputer, is that time often does not go linearly in these data sets. What you want is a smooth timeline like the one shown in red on the top. But what we often get is a timeline that looks more like the bottom. And the reason for this is it's quite expensive for scientists to run simulations or to collect data. So they don't do it at regular time intervals. They'll often collect more data when there's something interesting happening and less data when there isn't much changing or isn't much interesting happening. But that causes challenges as well, because if you consider each one of these a frame, as is traditionally done, then you get time moving all over the place, things speeding up and slowing down. So time often needs to be rescaled and resampled. Here is one data set that we worked with where I'm just showing kind of the raw data points without any additional design on top. And one of the things that you might notice is that time seems to speed up about halfway through. I'm not sure if with the zoom lag you can see that, but it kind of starts slowly and then speeds up by the end. Before I tell you more about this, I want to show you what the final visualization looked like. So, we obviously added a lot of design elements. We added lighting and textures and a background of a starry night sky. We turned all of the points into either a solid, liquid, or a gas, depending on the temperature of that point and its material properties at that given time, which are in the data. We slowed this down by a lot. We wanted to make it feel, very large because these are two planets. We are in space. We wanted to make it feel large and slow and exciting. So we slowed down the data set, and we also designed this exciting camera move around it that gets us right up close to the data. I always called this moment in it as the audience getting hit in the face with this blob. We did really want to try to make it, more exciting and more immersive and to feel large and imposing. So again, going back to kind of just what the data itself looked like, the reason that time speeds up halfway through is because the scientist was more interested in studying the initial impact of these two planets. So she wrote out more data at first, and then as things kind of got less exciting towards the end, she wrote out less data. So what we had to do in order to kind of make time move linearly is looking at the data attributes. Specifically, the time and velocity. We did what's called advection interpolation, where at each point we interpolate the data point both forwards and backwards, and then figure out where it should be at the exact time that we want it to be. Oh, and I do have an example of that. And here's kind of what the final difference looked like. A challenge with this type of interpolation is that sometimes you get jumpy motion. There are many different interpolation algorithms, so sometimes it requires trying several of them to see what makes motion look smooth. Another challenge is data is often represented in complex coordinate systems. So even something as simple as the Earth or creating a map, data can be represented in all of these different ways and more. These are just images that I took from Wikipedia. A lot of these are things that you might not have seen that might be more efficient for one reason or another. We often see like Cartesian coordinate systems, but those are not always the most efficient. And this isn't just true for representing globes and maps. All data comes in various formats, and scientists often choose a data format or invent a new data format that is just specific to their exact needs and their exact data set. Different scientific domains have different data representations. Here are just some of the kind of weirder formats that I've come across. So kind of the final challenge in this section I want to talk about is that there isn't actually a single software that does it all. Here you can see a bunch that are often in use. the kind of two main categories that are used are artistic software, where you see Maya, as well as Houdini, which are the main tools that, well, Maya, Houdini, and Blender are the main ones that are used in the industry. And then there's the broad category of scientific software and a lot of custom software as well. We often have to create pipelines that tie these different tools together, or we kind of pick and choose which one is most appropriate for a specific project. So kind of need to have expertise across all of these, as well as custom software development. One of the custom tools that my team at the Advanced Visualization Lab had developed is Party View, which is open source, and we use for what we call pre-visualization, which is a way to just downsample the data because it's often, huge and can take minutes to load a single file. So we downsample it and represent it in a much more simple way so that we get just enough information that we can start working on designing the camera and designing the speed and the timing of the data. So this is usually where we start our pipeline. Then, as mentioned in the earlier video, there's a tool that we've also developed called Virtual Director, which is a way that we literally fly around the data kind of with a joystick, this 3D mouse controller that helps us create more natural camera moves rather than creating keyframes that we interpolate between. We find that those often feel very algorithmic, and we prefer to perform a camera move so that the camera feels more like it's reacting to what's happening in the data. Like if there's an explosion, you kind of like maybe jump back, and it feels more natural. And here's a recording of Virtual Director. And we can see, again, this kind of downsampled version, simplified of the data set. Now we jump off of the camera path and we can see the camera in front of us that we have just performed. We can go in and edit any of the keys and turn on a little television view so we can see what the camera is seeing. So this is how we have always designed our camera moves and find it a very intuitive way and natural way to perform these camera paths. A challenge in working with this broad category of artistic software is that the types of data formats that are supported are pretty limited. And as I mentioned, scientific data can come in of a variety of weird formats that are not natively understood by the software. So typically, if we're talking about, say, volumetric data, artistic software expects the data to be in a uniform grid. But here on the right, I'm showing a stretched grid, which is quite common in scientific data, or a nested multi-resolution grid, which is something that is very common in astronomical data, or cylindrical or spherical grids, or any number of weird shapes. So in order to work with artistic software like Maya, we often have to sample the data. And there's a big question of, well, what's the right amount of sampling? If we use the finest data resolution, that often is not efficient. We kind of have to think about, well, where is the camera actually looking? What is reasonable for us to sample so that we get enough resolution, but we're not wasting resources on data that is smaller than what we could see. If we use, kind of just a middle resolution, we might lose too much data. Often in these data sets, there is more resolution where there's more interesting things happening. So, you don't necessarily want to just pick a middle resolution because the small stuff is the interesting stuff. So there's always this balance and a lot of data processing and testing and going back and forth and, designing a camera and then going back to the data to reprocess it to figure out how to get it to look right and to be represented in a way that we can actually work with it in this software. But as I mentioned, the artistic software, Maya and Houdini, are the main ones that are primarily used, but sometimes we also use scientific software if the data set is perhaps just way too complicated. But using scientific and artistic software has its pros and its cons. They essentially are polar opposites in terms of all of the things that we need the software to do. We want data analysis, we want to run on supercomputers. I was working at the National Center for Supercomputing Applications at the time, so this was important. So we want something that does all of these, and scientific and artistic tools kind of each do half of the work. So sometimes we create middleware or pipelines that involve both, or just kind of pick one or the other and take some losses. So this is an interesting challenge that we have to kind of solve with every new project. Now let's move on to the final type of challenge, design challenges. So the types of data visualizations I've been showing you are all cinematic, which is not, a traditional type of an analytical visualization style. So what exactly is it that makes a data visualization cinematic? No matter what type of visualization you're making, even if it's a bar chart, you have to answer questions like, how will you represent the data? What aspects of the data do you want to highlight? What colors will you use? There's kind of a common set of questions and design challenges that also apply to cinematic visualization. But in addition to the basic questions, cinematic visualization design requires some work on top of that. We also need to think about designing the overall scene and the environment. We don't just usually show one data set on its own. We kind of put it into a context, which might involve combining multiple data sets. We choreograph a camera. We figure out, what's in the frame and how to compose it. So things that are more commonly found in filmmaking. I want to demonstrate this with an example of a traditional visualization. This is not cinematic. This is a visualization that was created by scientists of this photosynthetic organelle called a chromatophore. So this is telling the story of photosynthesis, which I touched on earlier in these organelles. And the scientists had created this kind of simplified way of telling the story. And we wanted to take this same data set and tell the same story, but to make it exciting and to make it immersive for a planetarium dome show. And we wanted it to be understandable to audiences of all ages. So how did we do that? We started by creating a context. So rather than just showing this, weird object on its own, we made millions of copies of it and organized them into the shapes of the bacteria in which they're commonly found. And this bacteria shape is perhaps, more familiar to the audience than the shape of the chromatophore itself. So we're establishing context, grounding it in something a bit more familiar. And we don't just show all of the data at once. We kind of zoom in slowly, and then we fade into this kind of more X-ray view where we're seeing inside. So we slowly increase the amount of detail while there's a narration happening, letting the audience, acclimate to what they've seen so far before introducing new information. And only once we set all of this up, we finally see a ray of light hit the chromatophore and the process of photosynthesis begins. And then we follow it through at that point. So all of this setup and context is incredibly important for this work. So I want to talk about a few rules from cinema that we apply to visualization as well. If anyone in the audience is a photographer or filmmaker, you're probably familiar with the rule of thirds. Essentially, this just means that humans tend to find images more pleasing, not if they're centered, but if they're aligned with the 1/3 and 2/3 lines in an image. So here we're placing the Earth kind of right at this intersection. And even though you might think that the entire left 1/3 is wasted because it's pretty much just black, not much going on there. This was actually an intentional choice to make this image more pleasing. One thing that we do differently from traditional visualization is we like to put the camera inside the data box. Here we're looking at the large scale structure of the universe in two different visualizations. Something that you see in more traditional scientific data visualization is kind of what we call universe in a box, where you just kind of see the whole data set from the outside and you spin around it. That's very, very common. We try to avoid that. We put the camera inside the data box, get the audience as close and as personal with the data as possible to make it more immersive, more exciting, to make the audience feel like they're really there. Camera lens effects are important to the work that we do and is something that is actually controversial in the world of data visualization because these degrade the image. The data itself is very crisp and precise and accurate, and what we're doing with effects like these is, blurring it and making it less accurate. And we feel that adding cinematic effects like this makes it more beautiful, more cinematic, more engaging, although at the expense of some of that accuracy. So that is kind of always a balance that we have to use carefully. Lighting is a very powerful tool that we use for drama. Starting out looking at the dark side of the earth allows us to do this dramatic reveal of these hurricanes. It just makes it feel a little bit more exciting, like, oh, what's about to happen? And then you see it and you're kind of just a little bit more blown away than if we just kind of started by showing you the bright side of the earth in general. Context is very important and something that we spend a lot of time on as well. Here is a data set that is visualized without any context. And just looking at this, it might be difficult for you to know what it is exactly that we're looking at. Kind of looks like an orange made out of liquid or something. What this actually is the inside of the sun. And in order to better communicate what this is, we had to combine this data set with a few other data sets. So here's what the final visualization looks like. We start by flying over the surface of the sun, which is another few data sets. And then we dive underneath that surface and then see these kind of rolling liquidy shapes. And this allows the audience again to start with seeing kind of the bigger picture before we dive in. So in order to create this visualization, I want to break down one screenshot from later on in the visualization where we are looking at an X-ray view through to the center of the sun, just to illustrate compositing and registration of multiple data sets. So here is the final image. In order to put this together, we started with a data set of solar surface. And with that data set, we had these data around sunspots, which we highlighted with these spikes that emphasize them. The next data set is solar surface data from Matthias Rempel, which came to us as a series of black and white rectangular images like the one in the corner here. So what we had to do was tile this around a sphere, and we started playing each tile at a different point in time so that you wouldn't necessarily see repeating patterns, and we tried to blend between the edges of the tile. We made part of that transparent. Then we added solar rim data from the Solar Dynamics Observatory, which is a telescope that is looking at the sun. We added a starry night sky background. And then finally, we put the data set inside. This is the actual data that we're trying to tell the story about, but needed to add all of this context to make it work. So let's see. Right. So this data set, oh, the video stopped playing. Visualized by the scientist looked like what you see in the bottom right. The main feature that we were trying to highlight with this visualization was the fact that these shapes in the middle, which the scientists referred to as bananas because they make that shape, actually rotate as they move. And this was not something that was just visible in the original volumetric data set. So to better highlight that and to better tell the story of these rotating solar bananas, we added streamers around them. So that required, creating some derivative data and tracing to make that more visible. So that summarizes the design challenges and all of the different types of challenges that I wanted to discuss with you today. If you are interested in reaching out or learning more or working together, feel free to email me at this address, but I'll wrap it up here for now and I'll take any questions. Thank you.
Amazing talk, Helena. I will definitely also add some of these documentaries to my wish list on streaming services. Definitely curious to look at some of these. Really fantastic work. We have some time for questions. Maybe we'll open it up if anyone has a question. You can raise your hand. If not, maybe I'll just start with one. You also mentioned working with not just, oh, sorry, Hans has a question, actually. Let's go ahead.
I just have I, these must take hours and hours and hours of time, and are you using a single, let's say, desktop to render these things, or are you doing multiple render farms, or like, how are you doing to actually make this timely?
It's, you're right, it is not timely, even with the resources that we do have. I still say we, but it is they. I left that group. But they did have a render farm that was local, that was just owned by this lab that a lot of this was rendered on. Sometimes these jobs required even more capacity than our own render farm. So we actually did have access to the supercomputer. As I mentioned, this was at the National Center for Supercomputing Applications, which is at the University of Illinois. So we were blessed with having access to that as well. We kind of saved that just for the especially big jobs, but essentially did have unlimited computing access. So I know that there are other teams that are I'm not aware of anyone creating something quite, like IMAX film quality level, just on a single desktop. But you certainly could create something that is still cinematic, maybe with a smaller cluster, not necessarily a supercomputer.
Yeah, that's what I was wondering. Is that what would us mere humans be able to do on our setup? So
I mean, I suppose
wonderful.
you could. It would just take a few days where you can't use your computer. So maybe kick something off over the week, over a long weekend, and you'd get a result by the end of it.
Right. Thank you. Fantastic stuff.
Thank you.
Yeah, so cool. I'll go next just because I was just curious whether it's within your 3 challenge spaces or what aspect of the work is like your favorite. Like, where do find like the excitement in your work with what you showed? It's so cool, by the way.
Thank you. All of it. My background is computer science, and when I started in the team, I was a programmer, so I did a lot of basically the technical challenges was my job when I started out. Now that I've gone back to school, I'm focusing a bit more on the communication side. As part of my PhD, I'm doing a lot of like user studies and surveys and qualitative analysis. So kind of shifting from the data side to the human side in my recent interests. So I do love it all, though. I'm just personally not an artist. I have no artistic skills myself. So that part of it, I leave to the people that are good at it. I appreciate good art and good design, but I'm not the person that can actually make it beautiful myself.
Well, thank you for sharing. And I'm sure the communication piece is probably one of the hardest parts. So kudos to your new journey.
Thank you.
All right, Justin.
All right, yeah, excellent talk, Kalina, and super cool work. I have a question about so near the end you were mentioning the making it look good stuff being sort of controversial in academic settings, or having stuff come across as kind of looking too fancy or too pretty, so that can't be real science. And do you have any sort of approaches or ways you think that we can make that that not be a negative in an academic context, and have people who care about how stuff looks in that way be seen as a positive, not not an academic negative?
Yeah, I'm trying to do some of that in my current research at the University of Utah. I mean, there is a lot of research already that exists that shows pretty definitively that people do trust more beautiful visualizations more than ugly ones, that beautiful visualizations are more memorable than ugly ones. Like, we do know that this is true for the public, but somehow, like, the academic viz community still gives a lot of pushback of like, well, you're fussing with the data a bit too much. It's not a true data visualization. And I don't know, I'm hoping to change those perceptions by, talking more about what actually goes into creating these. We're not just making stuff up. When we do in the planetary collision that I showed, when we made it like a solid, liquid, or gas, and we made things light up, that those were artistic decisions that were still driven on the data, right? Like it was based on the temperature. It was not just something we were like, oh, well, let's just make this part bright. So I think and I hope that by starting to publish more about this work and talk more about it and trying to be more in these academic circles myself as a researcher now, not just a practitioner, that hopefully those perceptions will change as people start to understand what actually goes into making these. But I don't know. I'm early in this process.
Awesome. Hans?
It's really interesting. This is a very interesting conversation. It parallels it just I just noticed this parallel to research we've done in trust. So we developed a lot of technologies that they're like black box technologies. You hit a button, all of a sudden something is automatically generated for you. And some of the research that we've done is in getting trust from the user, and they are accepting of black box generations like that if they can go in and they can understand, okay, how is this calculated? What were the formulas used? Like the details. And then when they see that and they see how it was produced, generated, then they're more trusting, and more trusting further on when you're to use that tool as a black box tool. As long as when they do the sniff test, they go, wait, something looks funny. I want to expose it for a second and see, oh, okay, I'm okay with that now. I understand it. And so it feels like a similar thing to this visualization. It's like, yeah, the visualization is telling me something, but I don't trust it yet. So figuring out what that exposure needed to provide the trust is going to be interesting.
Yeah, one of the studies that I'm designing right now is related to that. I'm hoping to find better ways to communicate to audiences that what they're looking at is a visualization. Typically, they see this in, say, a film, and they're just told via narration, this is a data visualization. And first of all, do they know what that means? Does that mean anything to them? What do they understand when they hear that? And then even if they do understand it, do they care? Does that make a difference? And then other than just saying it verbally, what are some visual ways that we can convey that, what they're looking at is a visualization without detracting from the immersive experience? We wouldn't just want to add a bunch of like axes and color bars and like distracting kind of more data visi elements, because that detracts from the experience. But are there other ways that we could visually convey that this is data while still balancing the emotional and aesthetic appeal? So I'm trying to study that at the moment.
All right. Jiu?
Yeah, maybe room for one more. In your more recent UX findings, are you getting more insight into ways you can evaluate the educational impact of cinematic visualization projects on different audience members? Because I thought it was fascinating how your target age audience ranged from, 8 years old to like senior folks. So yeah, are you finding that there are ways to evaluate impact?
I haven't personally studied the education aspect of it, like how much people are learning from this. I've been more focused on like understanding and trust and credibility. I know that back when I was at University of Illinois, we did collaborate with educators who like created supplementary educational materials and did some like testing with school children. But that's not something that I'm personally involved with or have researched on my own.
Yeah, and so in terms of like iterating on your work and when you review the work post-production, what are some ways you can incorporate feedback back into the next versions?
Yeah, it's unfortunate that a lot of the feedback comes just after it's already finished, right? It would be great to get feedback like, well, you can still make changes to it, but you can't really show it to an audience and have them understand it until it's finished. So there's like a chicken and egg thing. So most of the feedback that we do get is on the finished products, which then we can't go and edit and fix. But we do try to take those learnings. Like the most kind of the thing that sparked me to go back to school to work on my PhD was this finding from just like comments on some of our videos and reviews, that people often thought that these visualizations were fake. They were like, oh, this is CGI, this is fake, like it's not real. And I was like, what do you mean it is real? Just because it's CGI doesn't mean it's not real. But like I get where they're coming from. So it just kind of, this more informal or qualitative feedback often gives us kind of just new research directions, or just like, oh, hey, this is a like a big problem overall. Even if, the comment was on a astronomy visualization and the next one that we're working on is a biology visualization, these types of things at a high level are still something to be aware of. Like, okay, if people think this is fake, then how can we better communicate that it's based on data, or, get to the bottom of why that is. So yeah, that's what I'm basically trying to find out.
Okay. Thank you.
Any other questions? Maybe in the meantime, I'll ask one. Kalina, I'm wondering a bit about like the different disciplines. Maybe this was sort of touched upon already in previous questions, but like, scientists, artists, they're very different. They think very differently. I guess you're sort of in the middle there. Like, I wonder if there's like, if you can reflect a bit on some of these maybe disciplinary challenges as well, with like getting these people to agree on like the direction, work together in ways where they think very differently or educated very differently. I don't know if that's something you encountered as well.
Yes, all the time. So for each visualization, we work with like a different science team. And sometimes it's really nice to work with scientists because they're like, well, you're the expert, I trust you and how to make these decisions. They provide guidance and feedback, and that's great. But a lot of times, scientists will be very set in their ways and be like, well, this is how we do it in our field. We love the rainbow color map. Everyone knows what this means. Or, and then we go like, yes, maybe to the experts, this makes sense, but to somebody who's seeing this for the first time and not familiar with this, like, we really want to do it this way. And, sometimes there's a bit of headbutting there. But it is always interesting too, because we do speak very different language. The word model means very different things, for example, and like the word simulation. And there's like, even when we're using some of the same vocabulary, we're using it in different ways. Like to a computer graphics person, a model is like a 3D shape. I could have a model of this mouse, but to a scientist, a model is like a mathematical representation of how something works. Which, I mean, I guess you could say that, I could make a mathematical representation of this too. It's related concept, but that's, the words are used very differently. Sometimes we think we're talking about the same thing, but we're actually talking about different things. So it is always a challenge, but it's fun to always learn from the scientists. That's what I love about this type of work, is that with every project, I learn a little bit more about something totally random. So always challenges.
Excellent. Yeah, that's really interesting. Yeah, hearing those insights also, and like how that dynamic works. Great. If there's no other questions.
There was one question in the chat from Alan Green.
Oh.
I thought was a pretty good question, so I want to make sure it gets there.
Sure. Let's see. Oh yeah, so he was asking how, what is it, 100,000 hours of compute works in reality with the satellite images of the Arctic.
So 100,000 hours, things are still calculated in hours, but it's, run across like 100,000 computers. So, you can run, well, I don't know how many computers, probably not as many as 100,000, but, thousands of computers. So each one runs for a few hours. So you get, a total amount that is quite a large number, but typically we often would run things overnight, not necessarily on the whole supercomputer, but like on our cluster, and we'd get like a whole video by the end of it. Or in the case of, it was actually 1.5 billion hours of compute time that took the scientists to assemble that one Arctic data set. I believe that did take them months on the supercomputer, but it was still, quite fast, not the 30 years or whatever that it sounds like.
Awesome. Yeah, that's great. Excellent. Yeah. With that, I think we can thank Kalina for a fantastic talk with lots of eye candy. So yeah, thank you so much again. Really, really exciting. And thanks everyone for engaging in the discussion.
Thank you for introducing us to the speaker, and Kalina for joining us.
Thanks.
Bye, everyone.
Thank you. Bye-bye.